In this lecture, we discuss about Gaussian bivariate random variables. So in the previous module, we have discussed about the normal distribution as well as the standard normal distribution. So the other name of a normal distribution is a Gaussian distribution. So the same Gaussian distribution, we'll consider it for the bivariate random variables. So here we consider the standard normal distribution. So x is called the normal variate, z is called the standard normal variate. So we have discussed what is the difference between the normal distribution as well as the standard normal distribution. Okay, for the standard normal distribution, always mean is equal to 0 and standard deviation is 1. Okay, so here we consider the two bivariate random variables, say z1 and z2, with outcomes anywhere in this z1 z2 plane, so that z1 z2 lies between minus infinity and plus infinity. Here the normalized Gaussian bivariate PDF, that is the PDF of the Gaussian bivariate random variable with respect to z1 and z2, is given by f z1 of z2, f z1 z2 of z1 z2, which is equal to 1 by 2 pi times root of 1 minus rho z square into exponential of minus of z1 square minus 2 rho z into z1 z2 plus z2 square whole divided by 2 into 1 minus rho z square. The entire quantity comes in the, this is the complete exponent. This is the complete exponent, e raised to. Okay, please try to remember the PDF. That is, this is the representation. Already we know how we represent the PDF of a two bivariate random variable. Suffix we use the capital letter f z1 z2 of z1 z2, which is equal to, this is the multiple, exponential of, this is the exponent. Okay, now let us here we have the condition, that is rho z is always less than 1 and square root of 1 minus rho z square is greater than 0. So let us prove 1, or the PDF of normalized Gaussian bivariate PDF, which we have defined, is a PDF. So always we know, in order to show any function is a PDF, this since it is a continuous probability distribution, so we have to show integral between the limits is equal to 1. Since it is a bivariate, so double integral of minus infinity to plus infinity f z1 z2 of z1 z2 is equal to 1. Okay, so let us show 1 is a PDF. So to show 1 is a PDF, here what I will do is, I will consider the marginal distribution, marginal PDFs. Okay, marginal PDFs of z1 z2. Okay, so marginal PDF we know of z1, it is defined to be integral from minus infinity to plus infinity f z1 z2 of z1 z2 dz2. So I have given already the general formula. So here x and y are replaced by z1 z2. So first let us prove this integral, that is the marginal PDF of z1, okay, is equal to integral from minus infinity to plus infinity f of z1 z2 dz2. Means we have to integrate the normalized PDF with respect to z2. So before evaluating this integral between minus infinity to plus infinity, so let us simplify the PDF. Since we have the PDF here, we have the PDF in the form that is 1 by 2 pi times root of 1 minus rho z square exponential of the exponent. Here we have an algebraic expression, okay, that is z1 square minus 2 rho z z1 z2 plus z2 square. So to evaluate the integral with respect to z2, so here we can take the z1 term, or we can consider the z1 terms are constants. So let us simplify this exponent with the help of completing the square. So here, to simplify this PDF, to integrate with respect to z1 or with respect to z2, we have to use the technique of completing the square. So already I have shown the how to use or how to do the completing the square technique many a times, and also in one of the example I have shown in the previous topic. Please go through it, you will understand. See here, directly I have written, after using the technique of completing the square, I have written the PDF 1 in the form, since we have to integrate with respect to z2, so I have taken the z1 term outside, that is e power minus z1 square by 2 divided by 2 pi times root of 1 minus rho z square times exponential of minus z2 minus rho z z1 whole square divided by 2 times of 1 minus rho z2 rho z square. So now this is easy to integrate. See, let us substitute this PDF in this marginal PDF. Here on the RHS, let us substitute the PDF. So now which takes the form, the integral takes the form 2. So all the constant terms I have taken outside the integral sign, that is all z, that is how much I can take the z1 terms, that is z1 terms, and also the other terms. Okay, now the integrand is only exponential of some quantity. Now it is easy to integrate. Okay, so here to integrate this, to integrate the RHS, we have to use the standard substitution. Okay, so already I have shown the already this type of integral I have evaluated. Okay, so to evaluate this integrand or this integral, so here we have to consider the change of variable. Okay, the complete exponent will go for the substitution. Okay, and it will reduce this to integral from minus infinity to plus infinity e power minus u square by 2 du. Okay, so you can see how I have taken the substitution, the complete exponent, okay, that is u, differentiating with respect to z2, which gives du is equal to dz2 divided by root of 1 minus rho z square. Now making this substitution in 2, which reduces to f z1 of z1 is equal to e power minus z1 square by 2 divided by 2 pi times integral from minus infinity to plus infinity e power minus u square by 2 du. Okay, so already I have proved this integral in the previous example. Okay, in the form of a note I have given. So this is a very simple way of evaluating using the technique of gamma function. Okay, now we have to just this is an improper integral, just we have to bring this integral in the standard form, and we have to use the gamma functions to evaluate. The value of this integral gives root pi by root 2. Already I have proved this, you can see that example. So I have proved, okay, the derivation I have given you. Just please go through it. Okay, now I'll substitute the value, direct value, that is root pi by root 2. So we can say this is a standard integral. Always whenever we find this kind of integral, there we can use the value directly. Okay, the proof is very simple. Here I'll substitute the value. That is if z1 of z2 is equal to, substituting the value of this integral as root pi by root 2 and simplifying, which will reduce us to 1 by root 2 pi e power minus z1 square by 2. So you can see the RHS. So this complete function is nothing but the normalized PDF, right, with respect to Z1. Okay, in the same way, similarly, we can show the PDF of Z2 on the same way. In the same way, we can prove it, which also gives f Z2 of Z2 is equal to 1 by root 2 pi e power minus Z2 square by 2, where both Z1 and Z2 lies between minus infinity and plus infinity. Okay, now substituting 3 and 4, okay, which gives double integral from minus infinity to plus infinity f of z1 z2 z1 z2 dz1 dz2, which is equal to the PDF of the marginal is equal to marginal PDF of z2, which is equal to 1. Okay, so it is easy to verify. So 5 shows f z1 of z2 is a bivariate PDF. So therefore 3 and 4 are the PDFs of Gaussian random variable z1 and z2, we can say. So therefore we have the means and variance of the random variable z1 and z2. So as I said, Z stands for the standard normal variate. To define the PDF of the standard normal variate, always mean is 0 and standard deviation is equal to 1. So according to that, here z1 and z2 are the normalized Gaussian bivariate random variables. So therefore, automatically expectation of z1 is equal to expectation of z2. So we say these two are the means of z1 and z2. We denote it by mu z, which is equal to 0. And also, since the standard deviation is 1, so if it is 1, then variance of z1 and z2 are also equal to 1. That is, variance of z1 is equal to variance of z2 is equal to, we can represent with respect to z, that is rho z square is equal to 1. So this is easy to, already I have shown the derivation with respect to a single standard normal variate. Okay, in the same way you can prove this. So what we have learnt is, so what is a bivariate Gaussian normalized PDF and how it will be a PDF. We have shown the double integral of the PDF is equal to 1 using the marginal PDFs of Z1 and Z2. Okay, so the means and variance already we know, so we can just follow that. Now let us discuss about the correlations of the Gaussian normalized bivariate random variables. That is, by definition, the correlation of Z1 and Z2 is given by expectation of Z1 Z2 is equal to rho Z. Okay, so already we know this. So it is called as the correlation of normalized Gaussian bivariate random variables. So you can prove this with the help of the PDF. So in this case, the correlation coefficient and covariance are all equal. This also you can prove. That is, expectation of Z1 Z2 is nothing but the correlation factor. Covariance of Z1 Z2, rho Z stand for the that is the coefficient of correlation. Okay, that is correlation, covariance and correlation coefficient are all equal in normalized Gaussian bivariate random variables. So these parameters you can prove. So since we have defined, I have defined the PDF, you can prove these quantities or the parameters. And one more thing we have to discuss is the general Gaussian bivariate random variables. So what do you mean by general Gaussian bivariate random variables? So as I said, X stands for the normal variate and Z stands for the standard normal variate. Okay, so here we consider such relation between the normal variate and standard normal variate. So the relation is Z is equal to X minus mu by sigma. Okay. Now let us consider the general Gaussian bivariate random variable, that is x1 and x2. Okay, connected with the relation Z is equal to X minus mu by sigma. Okay, if we rewrite this expression, this one, if we rewrite this in terms of Z, which gives X is equal to sigma Z plus mu. Okay, so let us consider the same relation, that is z is equal to x minus. This is a standard relation. We call this relation as the relation between the standard normal variate and normal variate. So please remember, always x stand for normal variate, z stand for standard normal variate. So whenever we study the Gaussian random variables or Gaussian distribution. Okay. So now we are in bivariate random variables. So let us consider the two bivariate random variables x1 and x2. And with the help of this relation, we can write x1 and x2 in terms of standard normal variate as x1 is equal to rho x1 z1 plus mu x1, and x2 is equal to rho x2 z2 plus mu x2. As we know, rho x1, rho x2 are the standard distribution, or sorry, standard deviation of x1, x2. Mu x1 and mu x2 are means of x1, x2. So already we have proved the results also in single random variable. Let us find the covariance of the random variables x1 and x2. So we know the procedure how to find the covariance. That is, covariance of x1 x2 is given by covariance of x1 x2 is equal to expectation of x1 minus mu x1 into x2 minus mu x2. This is the general formula. Since we have considered the general x1 and x2 as the Gaussian random variables, so we have the relations 1 and 2. Let us substitute and simplify. Okay, I told you how to simplify this expectation by multiplying and then combining the like terms, then operating the expectation term by term, which gives rho x1, rho x2 times expectation of z1, z2. So expectation of z1 and z2 is nothing but rho z. So therefore, covariance of x1, x2 is equal to rho x1, rho x2 times rho z. The last thing we have with respect to the Gaussian bivariate random variable is independence and uncorrelated. So if the Gaussian random variable z1 and z2 are uncorrelated, then rho z is equal to 0. Then the PDF becomes simply the product of two Gaussian PDFs. See here I have shown. So then if the bivariate PDF is a product of two marginal PDFs, then we say that z1 and z2 are independent. Okay. In other words, we can say if the bivariate Gaussian random variables are uncorrelated, then they are independent. So hope you will follow this lecture and try to understand what do you mean by the normalized Gaussian random variable and the PDFs.